This is
Yes.
the laser, right? Okay,
Yeah.
got it. Thank you. Thank you. Thank you, Praveen. I am still, in spite of so much experience for this online presentation, I am still not so confident. Okay, now it is
No problem,
working.
Professor. Welcome. Go ahead. The stage is yours.
Okay, fine. Thank you. So first of all, I would like to thank Praveen Garu and his team for inviting me for this talk. As you will see that from the title also that it is little bit different from optics. Okay, it is not exactly in optics. It is a topic is actually a topic of various interdisciplinary topic of atomic physics, molecular physics, nuclear physics, and condensed matter physics. I come from condensed matter side. I've been doing this work for earlier I was only doing theory, but last 20 years I've been doing, my students have been doing experimental work also. So this is, or as you can see, shift heavy ion irradiation assisted silicon nanoparticle formation. These are my collaborators. In the title itself, you can see my co-authors here. Professor Nageshwar Rao is my colleague in the university, and all others are postdoc or students. And my other colleagues recently with whom I have been collaborating on this work are Nageshwar Rao, Venugopal Rao, and some other former students and present students. Okay, so motivation of ion, see the topic is ion beam related work for making the nanoparticles. Okay, basically the purpose of using ion beam is to do the irradiation, and then during irradiation it is having the interaction with the material, and then after that you have to do annealing to find the nanoparticles. But in general, motivation of ion beam processing is very broad based. For example, ion implantation and device applications, and then characterization. Starting with the scratch. Okay, nanomaterial is basically starting from atom, and when you go to the condenser, the full material, then you can see there are two approaches to form this nanomaterial: bottom up and top down. Bottom up is starting from atom or molecule, and then build up at nanoscale like 1 nanometer, 5 nanometer, and so on. Other is top down, means have the bulk material and then cut polish and with the specialized techniques, small sizes. And in both cases, as you can see that from here, these are the atomic energy levels, and this is the energy levels of the condensed bulk material. In each case, when you go from atomic levels to this nanomaterial, or you go from the top down, that is condensed matter, to this. In each case, the energy levels change, their energy gap and so on, either from atomic size. When there are too many atoms are put together, then this becomes the energy gap, and that is controlled by the size. Similarly, from the top down case, when you cut polish, then again the size changes, then energy levels and energy band gap changes. For example, as soon as the size becomes less than Bohr excitron diameter, for example, here this is when the size has come just exactly to Bohr excitron diameter, and then it goes further down. Then the energy levels, because the particle has to be confined in that size, or electrons have to confine in that size, so the energy band gap changes, and that energy band gap is given by this expression. This is the energy band gap of the nanomaterial. It is related to the energy band gap of bulk material through the size k by d square. So as d decreases, the band gap increases. Basically, it is band gap engineering. You can engineer the band gap by changing the size. Okay, and then to synthesize and characterize, there are various methods. Sputtering method, atom beam sputtering, or magnetron sputtering, and then there is ion implantation. These are the main methods which are used normally. And after, when you make the particle, deposit the material, you don't get nanoparticle, then you have to do the post-deposition treatments. And that is the crucial part: rapid thermal annealing, nuclear furnace annealing, microwave annealing, shift heavy ion irradiation annealing. The purpose of these techniques is to anneal them, anneal the material which you have deposited by sputtering or implantation, and then after that you can anneal so that you get the nanoparticles. For example, this is magnetron sputtering, where you have a target for whatever you want to make the particles, and you have the substrate on this. This target is bombarded by the argon ion or various types of ions, and then it is depositing on the substrate. Okay. Basically, the purpose of sputtering is to sputter from the material and deposit on a substrate. That is the basic mechanism. And similarly, atom beam sputtering is also something similar, where atoms are accelerated to certain energy, and then they are colliding with the target, and the ejected thing they are deposited on the substrate. Okay, so whatever target you put on, here is the main advantage of all these techniques is that whatever you deposit on the target, if you want to have the composite method of depositing, then on, for example, silicon oxide or hafnium oxide, you deposit another germanium pieces or silica pieces, then you will get a composite substrate, and that you can study by various techniques. Then most important afterwards is the characterization technique. Rutherford backscattering, X-ray diffraction. For example, RBS scattering is the old technique. By that you can find out the composition and the depth distribution. Then X-ray diffraction, which tells you the structure. Raman spectrometry takes you about the photon properties, phonon properties. And TEM, finally, the method. After doing all the methods, final thing is TEM. TEM gives you exact information. For example, these days, if any paper you send by doing these techniques, if you have not done TEM, then it will come back, so, because that gives the most reliable information. TEM means you are seeing it directly. Okay, so let me give, because the audience is not in ion-solid interaction, so I have included some slides about basics of ion-solid interaction, and that is when an ion goes into the material, then it has two ways of losing its energy, and that lost energy is responsible for making the nanoparticles or annealing and so on. So electronic stopping and nuclear stopping. Electronic stopping is the energy is given to the target electronic structure, that is the free electrons as well as the core electrons of the material. And nuclear stopping is actually a misnomer. Nuclear stopping is nothing to do with the nucleus, but is actually the radiation damage. That is atomic phenomena. That is atoms are coming out of that, taking the energy from the projectile. And that depends on energy. When energy of the projectile is very high, then it is bare ion is moving, and you are having only the electronic stopping. First region, and then from that, as the energy is lost slowly, then it comes to the second region. So here the projectile is interacting with the entire system of the electrons. That is the collective excitation and so on. And then as energy is lost, then it comes back to the lower region where binary collisions are taking place. That is, the electrons of the target are one by one, that is binary collision between the electrons of the target and the projectile is creating the energy loss. Okay, and depending on, and then this is nuclear energy loss. That is, here when it has come to the lower, very low energy, then the electrons cannot be excited, electrons cannot be ionized. Then the energy is taken by the atoms of the material, and that is called the nuclear energy loss. So there is a collision cascade. One atom collides with this, and that happens only at the energy which is order of the binding energy of the atoms of the target. So then it is a collision cascade, and that is what is called nuclear energy. I am repeating that this is actually a misnomer. This has nothing to do with the nucleus. It is the radiation damage, basically. Okay, and that happens as the lower end of the energy. That is when energy becomes less. Okay. Then there is an important role played by the structure of the material. For example, if your incident ion is going along one of the crystallographic directions, this is random direction. If it's going along the crystallographic directions, then the particle will go deep inside and order of magnitude deeper. So for example, RBS scattering technique, RBS scattering spectrum will give you this is the incident ion going back and taking information from the material. So this is random for this case, in coming and going back. But as soon as the projectile is going along for one of the directions, projectile, that is the crystallographic planar direction or axial direction, then the yield, backscattering yield becomes order of magnitude less. And corresponding to that, the range becomes order of magnitude large. So this phenomena, what is called channeling, here is a point blank view of that. If the particle is going at low index, small angle with respect to one of the axial directions, then it will not collide directly with the atoms of the material, but it will collide only with the free electrons and outer electrons. Okay, so the yield will become order of magnitude less and range become order of magnitude large. So the desirability of this phenomena of channeling depends on what you want to do. If you want to study the material deep inside the material, then you want this phenomena to take place. But if you want to study only in the surface, then you want to avoid this. So you should know what are the order of angle that should be there for the phenomena to take place in channeling. So if the angle is smaller than about a degree, then it will always go into channeling. Only the surface atoms will scatter, and that angle can be actually calculated. For example, here the particle is coming at an angle psi, then its longitudinal velocity, that is V cosine psi, is most of the velocity, and the sine psi is very small. Psi is small. So in radians, for example, if psi is very small, of the order of a degree, then normal velocity is V psi, and longitudinal velocity is almost V. So during the motion of the particle at small angles, I repeat, that is about of the order of 1 degree, and that angle can be calculated. So about 1 degree or so, then if it will be not seeing the individual structure of the atoms along this direction. When it is moving, then it will not see the individual structure, but it will see only the continuum potential due to all the atoms along with that direction from 1, 0, whatever is the HKL plane or axis. And that gives the condition that R minimum is the minimum distance of approach. So if this time is greater than the time required to go inside, if the time that is collision time with one atom is larger than the time required to go from one atom to the other, then it will not see this individual structure. It will see only the continuum potential. And once that happens, then the calculation, the potential is actually the average of the potential along that direction, the axial potential or the planar potential. In each case, you can find the that condition gives you, this condition gives you the angle. That is this condition for continuum potential. That gives you the angle which should be there for channeling to take place. So if psi is less than psi 1, for example, if you put the numbers here, Z1, let's say alpha particles, is silicon, whatever you put, it comes off the order of about a degree. But it of course depends on the energy of the particle. If energy is large, channeling angle is small, critical angle is small. If energy is small, critical angle is large. But normal MEV particles, it is of the order of 1 degree. But if you go to the relativistic energy, then it's very small. So that case, if the angle is less than that, then the particle will channel and the range will become very large. But if it is more than that, then it will not. So you have to choose it depending on the experiment what you want to do. But during the channeling phenomena, there are very interesting phenomena takes place that one has to take care whenever you do experiment on that. And that is as you increase the projectile charge, starting from alpha particle, helium particle, then lithium, beryllium, and so on. Then one sees that for channeling situation, there is a oscillation in the stopping power. For example, this is very interesting phenomena that for some of these Z1s, the target is almost transparent. You can see energy loss d by dx is very small. And if you go to some of the other Z1s, then for less or more, this stopping is normal. And that is independent of the target. For example, if you instead of silicon, if you have this gold in same places, the minimum takes place around 10 and next minimum takes place around about 30 and so on. So for those Z1s, that is projectiles, for those Z1, that is projectile, the target is almost transparent along the channeling direction, okay? And this is very simple phenomena which comes from atomic physics. I will not go to details of that. But basically what one sees is that stopping, which is due to the binary collision, it is at lower energy, the binary collision between the target electrons and the projectile, that can be modeled in terms of g by dx by nm d square qd, this is momentum transfer cross section. And that depends on various phase shifts. So the effective potential is not UR, but depending on the partial wave L is equal to 0 S wave, P wave, D wave. This is the effective potential. And the effective potential, if it becomes, as you increase Z, because this depends on Z1 and Z2. So Z1, as you increase Z1, the effective potential increases, and then that particle which is moving, it can support a bound state. This is the attractive potential for the electrons with that the projectile. So for L is equal to 0 S wave, it is the normal, but as you go to L is equal to 1 or 2, P wave, D wave, there comes a Z1 for which it becomes negative and it becomes positive below that, okay? So as soon as the particle becomes Z1 is larger, then it is able to support a bound state of that. And that decides what will be the momentum transfer cross section. So that's what these oscillations in stopping power, they are directly related to the filling of the periodic shells. For example, here, for example, at about Z1 is equal to 6, 2p state is filled for the first time. 3D state is filled for the first time in the period. If you remember periodic table, then 3D state is filled here, 2p state is filled. So depending on the 2p, 3D states, you can see at that exactly at those places, this potential becomes effectively negative, and it creates the resonance scattering, and that's why the maxima takes place at those places. And what is basically one is doing atomic physics in solids, because the only free electrons are involved in during the motion, outermost free electrons. And this interesting phenomena has been observed. That's why whenever you do any experiment, one has to take care of this. Okay, and then so this is taking care of that. Now the techniques that are used are Rutherford backscattering and elastic recoil detection analysis. Rutherford backscattering is that basically your projectile goes, interacts with the target, and comes back scattered. Okay, basically what is happening is that you send the alpha particle or whatever particle you want to study, whatever you want to use as a probe particle. Here it is 3 MeV alpha particle, and it scatters from the target and comes back. So here the Rutherford backscattering philosophy is that the projectile goes and brings back the information in terms of the kinematical factor. Okay, that is what is happening inside the material is taken by the projectile and after scattering. That is Rutherford backscattering. And the complementary technique is elastic recoil detection analysis. In which what happens is that the ion beam goes and then it displaces the particles inside the material, and those places which are recoiled one, they bring back the information. So the two things, this case, that is the kinematical factor for the ERDA and kinematical factor of the Rutherford backscattering. They are complementary. In one case, information is given by the collected and given by the projectile. In another case, information is taken by the projectile, this elastically recoiled materials, and they bring back the information. So the information that can be collected by Rutherford backscattering is complemented by, this is complementary to ERDA and so on. Okay, so then I will spend 1 or 2 minutes about what can we do about the various compounds in the semiconductors, because ultimately silicon and germanium are the things that we have been studying. So, for example, if you have two material, there is a substrate of gallium arsenide, and on that if you deposit indium gallium arsenide or aluminum gallium arsenide here, okay, there is a gallium arsenide substrate and indium gallium arsenide or aluminum gallium arsenide. So their lattice parameters are different, and then when there is a different lattice parameters corresponding to that, here is gallium arsenide, then you have indium arsenide, and their energy band gaps are different. So if there is a material which is made from both of them, that is on the you deposit on indium gallium arsenide and gallium arsenide, you have some fraction of indium on this, and some fraction of gallium on that, then the energy band gap is different. This, okay, and that's very important in the band gap engineering and up to electronic analysis, up to electronic devices. So, but what is the problem is that when you have the different energy band gap, at the same time you have different lattice parameters. So that gives rise to this, there is a mismatch between the materials, and that mismatch gives you the interaction, it gives you the strain. And that strain, depending on whether it is more or less strain, gives you either tensile strain or compressive strain. And that strain directly reflects in the scattering phenomena. For example, here the lattice matched, and here is strain material. And strain material, if you have scattering done by this strain material, then you get a scattered thing, which is that gives you the angle between the two, and that can directly give you information about the strain from the full width analysis of full width of half maximum distance, and that gives you the information about the whole thing. Okay, that is the how much strain is there, and that strain is very crucial for calculating the energy band gap engineering and so on. So this is for the compound semiconductors. And in that case, suppose you have such a material, you can see here you have a gallium arsenide here and surrounded by aluminum gallium arsenide and on both the sides. So aluminum gallium arsenide has this much band gap. Here it is this much band gap, and the gallium arsenide has this. So if there is a particle which is outside the energy band gap in gallium arsenide, but surrounded by the aluminum gallium arsenide on both sides, then it is confined. Confinement of that that gives rise to energy particle in a box, for example. And that is the basis of this quantum well and quantum dot and quantum wire and so on. Because if it is surrounded by two sides, then it becomes quantum. One side is quantum well, quantum wire, and quantum dot is surrounded by all sides. And this is the basic of the quantum confinement, which gives rise to something which is called band gap engineering. Okay. For example, just some few results from this kind of thing. Indium gallium arsenide heterostructures. So the thickness of the material is, let's say, small 12 to 36, 16, and 96 nanometers. Okay, and there are the indium composition is X is 0.1, there's 1%, 15%, and 20%, and 25%. Then, depending on the difference of the strain can be because of the smallness of the thickness. If the thickness is very small, then it is completely strained. But if thickness is increases, then the strain degenerates into the defects. Okay, and that can be found out by experiment, which is by irradiating by the external ions. For example, if you have irradiated by the silver ion beams, high energy, then that changes the strain. For example, you have 12 nanometer. I hope I have made it clear that here the thickness, here this is 12 nanometers or 36 nanometers and so on. So depending on thickness of the material, you can unirradiated and irradiated. So as you change the thickness, then the strain, which is the ratio of the lattice parameters of the two materials, that strain increases by irradiation for the thin material, thin 12 nanometers, 36 nanometers. But if you go to the thicker one, then it is decreases, because in this case, defects are created and generated, and then those defects take away all the strain. So strain is decreasing here. Whereas here strain is increasing because there are no defects created in the thin materials. And that has been studied by us some time back. It will just give information about what can be done by the nuclear beams. Thin heterostructures of indium gallium arsenide result in reduced defect density, increased strain. Similarly, if you have a multi-quantum wells, instead of having one quantum well, you can have 20 periods of 20 nanometers each and 15 periods. Then again, something similar can be done by using the high energy silver ions and high energy gold ions. Here, these two different things is, here the energy is, fluence is larger, and here energy loss is larger. Here 200 MeV, 150 MeV. So here more energy is given, here more fluence. Fluence means number of particles which are colliding. And the effect of in this mixing is more of the fluence rather than the energy deposition. Number of atoms which are number of energy silver or gold ions. That is, fluence is more important than the number of than the energy. So that is the purpose of this, that the incident on fluence is more effective in mixing than the energy loss of the ions. Okay, now coming back to the main topic, that is synthesis of nanocrystals. This can be done by atom beam sputtering or ion implantation. Excuse me. So, but what one does is that by first one deposits either of these techniques and then irradiate. Okay, that is, while doing the sputtering or ion implantation, you have to do the irradiation to make the nanoparticles. And in that case, I'll show you the results here. This is the as deposited material. Then this is annealed at 700 and 800 degrees centigrade. So by annealing, you get the nanoparticles. And then after that, you can annealing results gives you here. And then you irradiate 100 MeV gold and 70 MeV nickel, and they are irradiated. And after that, when you do the irradiation here, with this, what is your fluence 5 into 10 to the 12, 2 into 10 to the 12, 5 into 10 to the 12, and this is 20 to the 13. So in this case, as a function of fluence, function of irradiation fluence, you can see that the size of the nanoparticle, which is determined by the TEM or any other method, you can see that as a function of fluence, the size of nanoparticle here is increasing. That is 2e to the 12, 23 nanometers where germanium. And this is method is here it is either sputtering by the source or the method of making the nanoparticles by doing the annealing by ion beams. Sometimes people will ask, but why do you do the annealing by ion? Temperature annealing should be enough, but temperature annealing is not controllable. Ion beams you can have the energy, which is energy and fluence. It can be controlled, and here is the effect of that. As you have more and more fluence, larger and larger size is created. Same thing happens with ion implantation. Here also, I will just go to the final result. Here again, by the increasing the ion fluence, you increase the size of the nanoparticle which is deposited. Okay, the germanium nanoparticles implanted in silicon oxide. Okay, and then you can go to the further on. This is another thing which is I just want to mention in 1 minute, that if the nanoparticles are made by annealing, by ion beam radiation, then as a function of fluence, it is increasing the size. But if there are already existing nanoparticles, for example, here, there are already existing nanoparticles by 700 or 800 degree of annealing, RTA is done, and you already have the nanoparticles secreted, and then you do the irradiation. Okay, in that case, the size of the nanoparticles decreases as a function of fluence. You can see that already existing nanoparticles are there. Then if you change the fluence from zero fluence to this and this increase, then it is decreased. And the mechanism in the two cases is different. First part is you are making the nanoparticles by depositing through the this annealing thing. But here already existing nanoparticles are there, and they are being bombarded by the ion beams, and then they are stripping off these particles. So here it is decreasing with fluence, whereas in the case of formation nanoparticles, you are increasing the bit size, and same thing will happen in silicon. So let me go quickly to the main thing, which is topic of this talk, and that is hafnium oxide. Okay, hafnium oxide, synthesis of characterization of germanium nanocrystals in embedded in hafnium oxide. Hafnium oxide is a material which is very much useful these days because silicon oxide has very small dielectric constant. Titanium oxide has high dielectric constant, but the energy band gap is very small. So the medium is which has a reasonable dielectric constant, reasonable energy band gap. Why are we talking about the higher this thing? Because for the devices, you can either change the area, change the thickness, or change the dielectric constant. So if area is large, you cannot have many things on the same chip. Distance, the thickness is also has a lower limit. So when possibility of this is reduced, then you have to have a higher dielectric constant to have a higher C. And that's why high dielectric constant of HFO2 is very important. And this material is in use for last 10, 15 years. So in this, what one does is that hafnium oxide, silicon substrate, you deposit by various methods, as sputtering or ion implantation or whatever, and then you have the small thickness of the this 10 to 15 nanometers of germanium. And then in this case, irradiation gives you the, here for example, first annealing is done and then irradiation. Okay, so then this is rapid thermal RTA, and then here. So RTA, you get particles of 11 nanometers, 16 nanometers, and then irradiation gives you this change of that is change in the size. And then let me come to nanoparticles can also be done by laser ablation. Again, same thing, laser ablation, you make the nanoparticles and then do the ion irradiations. And again, you get the result that is as you increase the fluence, then you can see that the size decreases. Already existing nanoparticles, you increase the fluence, then size is decreasing. Okay, average nanoparticle size. This is main important of this talk, that if the nanoparticles are to be created by the ion beam radiation, then it is increasing with the fluence. Where if it is already existing nanoparticles are there, then the radiation decreases the size of the nanoparticles. And this finally, which is here, experimental details for the this silicon wafer. So what one does is here, that here is the sputtering machine in which you put this hafnium oxide target and silicon wafer. Co-sputtering is done. By doing the co-sputtering, hafnium oxide and silicon wafer, so about 30% of the area is 30% area is silicon, and hafnium oxide is the rest of the target. So when you do the sputtering, then you get these chains, TEM images of the silicon and HFO2. Okay, these are the results you get. But when you do the radiation, that is HFO nanoparticles have been formed as deposited, and then this chain-like structure is done for the hafnium oxide and silicon. And then if you do the irradiation, SHI, that is silver ion, 100 MeV silver ion irradiation, then that radiation gives you, now here if you remember again, I'm repeating, that radiation is the main mechanism to synthesize the nanoparticle, okay? Then as you increase the radiation fluence, the size of the silicon nanoparticle is increasing. Whereas in the previous results, when already existing nanoparticles were there for any material, in that case it was germanium, then existing nanoparticles decrease as you increase the fluence. But if the radiation is the mechanism to form the nanoparticles, then it increases the size because more and more nanoparticles are deposited. And so here, for example, HRTM that also shows the same thing. Here, EDS spectra here. So HFO, SI pristine, then SiO2 and Si3. Okay, these are the two samples. I increase the fluence, then the size of the nanoparticle is increasing. Please remember that this is just in opposite when existing nanoparticles are there, and then if you irradiate, then the size decreases because atoms are stripped off from the surface of the nanoparticle. And the corresponding results for the PL, etc., they also show the same thing. The results are summarized here. That is 100 MeV silver ion irradiation, silicon nanoparticles were found within the composite surface. Silicon nanoparticles increases from 4.2 to 7.6 nanometer with increase in the ion fluence here. Because here the ion beams are responsible to do the annealing and then form the nanoparticles. Whereas if there are existing nanoparticles, then ion beams will be taking away the atom from the surface of nanoparticles. There the size decreases as you increase the fluence. But here increase of fluence increases the size of nanoparticle. And the luminescence peak at 530 nanometers is attributed to the silicon nanoparticles within the HFO matrix core shell structure. And rate shift indicates the increase in the nanoparticle size because there is a from 420 to 530 nanometers. So this is an increase of the wavelength, that the rate shift, that shows that nanoparticle size has increased because of the radiation frequency. We are in the PL spectra. Okay. So this is the main conclusion, and then I think I will not go to the detail. This is nothing to do with, this is something which is very important, which was done in our group some time back. That is alignment, silicon nanowires. This is relevant to what is done in ACRAM. That is the finding out what are the possibilities of SERS, surface enhanced Raman scattering. By having the silicon nanostructures and depositing the silver on that, then you can change the surface, and that change of surface, that gives you the surface enhanced Raman scattering, and that increases the detection possibility by 1,000 times. That was published in Journal of Applied Physics by Vendamani, and she's now working in ACRAM. So this is very important, but it is not relevant to this topic. I just wanted to mention it, that by having increasing the surface by silver coated or silver capped silicon nanowires, you can increase the size, increase the accuracy of the detection, and this can be used for the detection of the explosives or detection in the airports and so on. That when that paper was published in Journal of Applied, they actually called us, and myself, Banu and Nageshwara, we had to answer lots of questions, and they were very happy. Immediately they accepted that paper. But this is not the topic of the talk today. I just wanted to mention it. Okay, thank you.
Thank you, Professor Anandji. Thank you so much. That was a very wonderful presentation.
Yeah, so, I had to rush it because I wanted to cover so many things, but give a glimpse of the material. And
I can understand that. Yeah.
Yeah.
So So next time maybe if you want to participate in future events, then we can give you a keynote speech. Then that will you will
then if I get about an hour, then I can do a better job. I
40
can do
minutes to
justice
1
with this
hour.
thing.
Yeah, then you can make it.
Yeah,
So
especially because I could see that the optics people are there, so I have to give some background of the basics of ion interaction, ion solid interaction, and so on. That's why some time went in that. So main
yeah,
topic I could not devote much, but I hope people are, my email address is there. People can contact me for any.
yeah. So we'll ask now if anyone have any question or comment. You can please ask Professor Anand. Anyone from audience or?
Pathak sir.
Bol Chaudhary Saab.
I just want to know, I saw a lot of interesting features of your material, especially gallium arsenide and other things.
Yeah,
And
that was the older work during gallium arsenide was actually done by Nagesh long back, and then afterwards gallium nitride.
So you are doing a lot of annealing and you are bombarding all these things and
yeah, annealing, there are two types of annealing, three types actually we do. One is the annealing by RTA, rapid thermal annealing, microwave annealing, and IV annealing. Three annealings we do.
So can you provide some sample? I can do terahertz study, especially conductivity and band gap study.
Oh yeah, that will be wonderful. Actually, we are having some collaboration with Danu and Sikkim people, and they are having nano laser.
Okay, let him do nano one, but if you give me, so we will do a different type of study for you.
Oh, sure, yeah, that will be wonderful. Because I am here now, so we can have more closer interaction. And that will be wonderful, yeah. I will certainly be happy. And my colleagues in Sikkim University will also be very wonderful. Terahertz, they have been talking of terahertz thing.
So we have a full-fledged facility now, and we are characterizing a lot of materials.
Yeah.
If possible, you can give me some of your potential material which I can study and we can.
Oh sure, yeah, sure, yeah.
Okay, sir. Thank you.
Thank you, Chaudhary Saab. We'll keep in touch.
Okay, sir.